Hello everyone! My name is Daniela Rus. I'm the director of the Computer Science and Artificial Intelligence Laboratory at MIT and Deputy Dean of Research in the Schwarzman College of Computing. And I'd like to welcome all of you to the Machine Learning Applications Talk Series at CSAIL. Today I am delighted to introduce Dragomir Anguelov, who is Distinguished Scientist and Head of Waymo Research at Waymo. Now, Dragomir goes by Drago, and he got his PhD at Stanford in 2005. He was advised by Professor Daphne Koller, and in addition to his work with Daphne, he collaborated extensively with Sebastian Thrun, and I believe that was the origin of his passion for autonomous vehicles. Now, in addition to his passion for autonomous vehicles, Drago has great passion for perception and computer vision and for machine learning. His work was on applying statistical methods to problems in computer vision, computer graphics, and robotics during his PhD thesis. He took the same passions after graduation, and he worked on Street View. He developed the winning solution for the 2014 ImageNet competition. He was a senior director of perception at Zoox. He also worked as a senior scientist on the visual search engine at like.com. Drago was at Google from 2007 to 2015 and joined Waymo in 2018. Now, before we start the talk, a few logistics. Please unmute yourselves. And if you have questions, please send them to Matt in the chat. Drago, the Waymo vehicles have driven over 10 million miles in autonomous mode, and this has captured the world's imagination. We so look forward to hearing about this from you. Please join me in giving Drago a warm MIT welcome. Drago, over to you.
Thank you so much, Daniela, for the kind introduction. Pleasure to be here. So I will tell you about some of the research in machine learning we do that we aim at pushing and scaling further our autonomous driving stack. For those that don't know Waymo, we're Alphabet's autonomous driving company. Our mission is to make it safe and easy to move people and goods around. And we're focusing on two categories, moving people, which we do with our Waymo One service, and moving goods, which covers these Class 8 trucks you see, and also local delivery. Over more than a decade, we have driven autonomously actually over 20 million miles on public roads and over 20 billion miles in simulation and across 25 cities in the US. So that's over 1,000 years of human driving experience that benefits all vehicles in the Waymo fleet. Since October 2020, we launched the world's first fully autonomous service with 100% of rides with no human driver in a suburb of Phoenix, Arizona. You can go there and hail a ride in a completely 100% autonomous vehicle and experience it even today. In August of 2021, we launched our Trusted Tester programs in San Francisco, which allows San Franciscans to hail an autonomous ride on our most newest platform, which is the Jaguar I-Pace vehicles, fully electric, and equipped with Waymo's 5th generation sensors and platform. And so I want to show you a short video illustrating the Waymo driver in action in San Francisco. So these scenes generally illustrate the typical challenges of urban driving. They're quite complex environments, and a lot of the interactions ultimately they include a lot of interactions with various types of agents in the environment and negotiations, whether this is a car that we're passing on while going over a bump in this narrow street, or you will see a bit later these pedestrians with whom we can negotiate who is passing and trying to courteously let them cross. There's a lot of busy intersections there. You can see cyclists cutting in and out around parked vehicles that we need to heed. Also, cyclist maneuvers that suggest intents of the cyclists that we ultimately are willing to accommodate. This is, by the way, fully autonomous driving. You can see on the top right there is a auto box showing this. Here you can see in the dark, the open door is quite well seen in LiDAR, even if it's not seen too well in cameras. And here you need to go around double parked vehicles and construction workers and so on. And this is actually a very common situation. You need to be able to identify, if you can see here in the icon, we've identified these people even on loading vehicles, and that the vehicles are doubly parked for a while, so we can safely pass them on the left, even when there could be oncoming traffic, right? So this just illustrates some of the common things that you're likely to see in dense urban environments where we drive a lot today, right? And let me just pass on to the next. I think that's one of the challenges, but there's more. So ultimately, we want our driver to handle diverse operating domains, dense urban, suburban freeway, different types of weather like fog, rain, snow, and more rare scenarios, some of which occur once every 100,000 miles or a million. This is one, I would say, middle type rare case where a vehicle on the left here will blow through the intersection on red, and our system is able to detect that and successfully stop and let it go, even though we have the right to work, right? So these are also things we need to deal with. And this is a talk ultimately about ML. I'm a machine learning person, and so the question is, how do we deal with all these things in an autonomous driving stack? Furthermore, a more ML first autonomous driving stack, we want to have data do as much work for us as possible, and learning from it can be a very scalable way of doing handling this diversity. And if you look at it as a machine learning person, you can say, okay, well, what is the self-driving problem defined as? You have some sensors, in our case, camera, LiDAR, radar, seeing 360 around the car, and you want to map the input of the sensors and potentially route to controls, steering and acceleration, driving the environment, be safe, make progress, and that's great. Now, the problem is, despite trying to do this, you could take just a neural network, take any cutting edge architecture, like some convolutional neural network or transformer even, right? And you can try to do this. And while it works for some common cases like lane following, even in the 80s, actually, there were successes with seminal work like Alvin to do lane following with deep nets. It does not scale to the rare examples of the kind I just showed you. Ultimately, this task is just difficult for this uniform network approach. Mapping from tens of frames that contain tens of millions of pixels or laser scans to robust decisions is pushing what today's machine learning can offer, right? And to address this issue, Waymo does a few things, and so do some of the leading autonomous vehicle companies. First, of course, everything we do comes with safety at its core. We want to make sure that what we do is a thoughtful and safety-conscious approach, safety principles and rollout. It is an integrated approach, first of all. At Waymo, we have designed the hardware and software in-house, and we leverage a trio of powerful sensors, camera, LiDAR, radar, two of which are active sensors. And active sensors like LiDAR, radar are a great safety feature because they ensure that if an object is out there, you're going to see it, right? And LiDAR and radar data typically has less variance than camera data. And that's because car shapes are pretty stable in LiDAR, right? And is seen by LiDAR. While car appearance in images and pixels can differ a lot based on different textures and so on. And so as a result, some of these models can learn more robustly with fewer training examples. Generally, I'm starting with the perception sensors because that's the foundation of the stack, right? And your perception along with your perception. If you don't detect the objects accurately, or you don't get your semantics right, then all your high-level reasoning will also suffer, right? And so you need to get the foundations right. And I'll just show you a little bit of Waymo's 5th generation LiDAR, and that is currently on our I-PACE vehicles and the trucks. It offers unparalleled point cloud density, resolution, and dramatically better than our previous generation. What we also use at Waymo is maps. So we use them as a prior. So it's not the immutable truth, right? Maps can always be changed in the future, and we need to be able to handle this, but it is still a great safety feature. Maps let us anticipate what happens in occluded parts of the scene. Furthermore, the map is dynamic, and we have mechanisms for cars to share observations across the entire fleet in real time, and that can be useful too. One more thing I will talk about is, of course, Waymo, as a principle, we are attempting to heavily leverage machine learning to learn as much as possible from the data we collect. Right? We have years of experience of driving and capturing diverse scenes of high resolution over time. And what's also great for the autonomous driving domain is that when we capture this data, we get a lot of examples of people driving, and some of them are expert at this task that we're trying to master, and this is very useful data to learn from. Being ML first means that we will first aspire to solve problems that arise using machine learning. And what that means is that if you see issues in the models, we would aspire to improve them and improve our data sets as opposed to add necessarily human and expert-based heuristics. The human and expert-based heuristics can be very effort-intensive and not so scalable. And however, by saying this, I don't mean that you can completely get rid of them. And because we have to deal with extremely rare cases, there could be very few examples in hundreds of thousands to millions of miles. That's where ML is not great, right? And just trying to learn that you should stay on the road when your vehicle may not be the best idea. So these are things that you can add as additional knowledge. And that can be quite beneficial, especially in handling the rare situations of us. Right? And so a good autonomous stack ultimately should leverage as fully as possible the strengths of ML while mitigating the weaknesses. So during my time at Waymo, as you can see in the picture, the scope of ML and specifically deep learning models has grown dramatically. And by now there are major machine learning components in every major system. Each of this model benefits from cutting edge model architectures and state-of-the-art research that both in the academic field and of course Waymo's teams as well. So just to ground this a little bit, here's a diagram of a classic, classic but also popular modular stack such as Waymo's. At this point, all of the self-driving companies that have high robustness and can deal with complex environments have a stack like this, right? So there's some modules. Typically, they are perception, behavior prediction, and planning models, although there's a tendency to bring closer planning and behavior prediction together, right? And so this modular design has several functions and benefits. So one of them is by adding intermediate outputs, or in some way you can think of them as the API between the modules, this allows you to perform model inspection and interpretability. So when you see the model make a particular decision, you can go in the intermediate outputs and try to diagnose, okay, well, why did this model make this decision? And this is key in getting understanding of what parts of the model or the data sets need to be improved to deal with the issue that you may have seen. Intermediate outputs allow also integration of expert logic and improving the training of ML models using self-supervision. And the design of the learned components in each module themselves capture key intuitions about the domain and the specific task, which leads to better generalization. So as the data flow through the system modules in an AV stack, typically there are a couple of key trends. So one of them is you go from tens of millions of pixels of scans, very dense data, to structure. objects, relationships, and trajectories higher up in the stack. And we also go right from readings in perspective view to typically to top-down Euclidean view, where it's easier to impose in reason about geometry and 3D geometry specifically. And easier, it's also empirically shown that it's easier to generalize in Euclidean space than in perspective space. And it's less data intensive to put these models to generalize. So there's some of these trends, and also in planning, typically the stack has a hierarchical structure in the planner so that it can deal effectively with long and short-term decisions. So you can have a router which specifies the high-level streets or segments you want to drive, and then the planner generates mid-level decisions or trajectories, and then the controller executes them. And that also contributes to a modular and hierarchical design in this case, and that makes it more generalizable, especially to the rare examples, right? So that's one of the most things in mind that you have. And just to illustrate the type of outputs, intermediate outputs that you can have. So perception, there's a whole bunch of possible outputs, probably familiar to you. And in behavior prediction, you can output trajectories or occupancy, spatiotemporal occupancy grids and occlusion models and so on. I think finding which of these use of which of these combination really leads to a performant overall system is a very active area of research today. So now with this introduction out of the way, I will talk and give highlights of our research that help further this machine learning first design agenda in the stack. And I will talk about several topics. First, mention some of our neural net architecture work. So neural net architecture, of course, designing and building in your domain knowledge into this architecture is key to improving generalization. And let's start with a standard 3D object detector that we published a couple of years ago already. It's a method we called multi-view fusion. And this is a LiDAR detector, and well-tuned variants of this model I'm going to show in a second are state-of-the-art on the task in the Waymo open dataset. So the main idea here is that LiDAR data can be viewed in two different representations. So there's the top-down view. We can think of it as a point cloud generated by a spin of the LiDAR. But you can also view it as a range image, right? So in the range image, the rows are the individual beams in the LiDAR, and the columns are the azimuth of when the LiDAR spun, right? And so each of these has complementary strengths. And the neighborhoods of each point, typically a lot of the operations are convolutions, and convolutions defined over a neighborhood. Here, the neighborhoods are very different and have different complementary strengths. And so the idea of our method at the time was, well, let's perform 2D convolutions in both spaces and combine the results. And the schematic of the model looks a bit like this. So we, generate local point cloud features, and then we bin them in both views and apply convolution in both the top-down grid in 2D and in the perspective kind of image grid as well. And then we fuse those, and when we apply a detector head, right? And that is more performant than doing either. But there is a problem. And the problem is typically, and this is common to all the methods that do this top-down view convolutions, is the complexity of this grows quadratically with the range, right? Because you look top-down, the range of your LiDAR now, especially modern LiDARs, can be several hundred meters. That's a lot. And quadratic dependency on that in a real-time system is not great, right? And so we had an agenda to try to design an architecture that does not have this dependency, right? While still retaining all the quality, if possible. And that was not straightforward, but it culminated in a paper this year in CVPR that on a model called range sparse view, range sparse net. And I'll describe to you the idea of this model. So the idea is, well, to do most of the dense computations over the raw sensor data, which is natively representing all the data you have, right? And so you do as much processing as possible on the range images, and so you can extract your features. But also, what you do is let's say you want to detect cars and pedestrians, you do foreground segmentation of the LiDAR points or scans that correspond to pedestrians and vehicles. And that's a small subset of the points. And this is the only set of points that you will now generate a sparse point cloud of. And we transform that point cloud to Euclidean space, knowing, well, the geometry transform. We don't have to learn it. That's not scalable, right? And not generalizable. We just apply it and we create the sparse point cloud. But now we can process this sparse point cloud with sparse convolutions and apply a box detector head, the details of which you can read in the model. And so this is a model that's carefully designed to avoid range dependence. It builds in knowledge of geometry that you don't have to learn, and it's extremely fast. And beyond being extremely fast, it's also very high performance. So it turns out we don't lose much performance at all. In fact, in some cases, potentially even gain. And this is the comparison of the model with both PVR-CNN, which was the state-of-the-art model on the Waymo open data set at the time, even though it was extremely much slower. And here's other representatives of one view or the other that I presented, or both. And this method dominates them all in terms of a combination of speed and accuracy. And here's a video of this single frame LiDAR detector. We capped the range at 200 meters for the purposes of this video. And you can see, if you really zoom in on those small cars, like it detects in very high fidelity pretty much all the vehicles, right? And so that's what I wanted to show for neural net architecture for 3D object detection. Let's switch to behavior prediction. So the challenge of behavior prediction is that there is an enormous number of possible futures for a road user, even before considering the road topology and interaction with others, right? So we wanted to illustrate somehow this diversity of possible things people can do. And we visualized 10,000 15-second vehicle track snippets obtained from our log perception data, right? And so here you can see some left turns, you can see some right turns, you can see a few U-turns, and then there's some strange trajectories as well on the right. And they have different speed profiles and so on, right? So it's quite a rich space of things one can do. And our solution at the time of dealing with this is to quantize this space into possible futures into a finite manageable set of anchor or template trajectories. And here you can see we clustered possible space of trajectories into 128 anchors using k-means, right? And then based on this idea, we designed a method called multipath, which parameterizes the output space in terms of these discrete anchors and then continuous uncertainty associated with the anchors, which I would call as a Gaussian mixture distribution over future trajectories, right? And so it naturally, intuitively captures these two types of uncertainty. So first, we decide which anchor trajectories are likely given the scene. And so you can think of it like on a high level, you can intuitively, maybe this is the intent of the person. Are they going to get gas or burgers, right? And then you model the control uncertainty, which in other words, given an intent, how the agent wants to get somewhere, right? And so at inference time, this decomposition amounts to classifying anchors and then regressing Gaussian uncertainty around each time step for that specific intent. Right. And at the time, we used rasterization of the map and the past agent histories, essentially render them all in a large image and apply convolutional neural networks, which was quite great as it reuses state-of-the-art research in, well, image understanding. However, there is some very unpleasant field of view, resolution, and compute trade-offs here again. Also, convolutional nets are not that well suited to model long-range interactions. For efficiency, people put small filters, but actually long-range interactions are core to the task of prediction. And so it helps to model them more explicitly than that. Otherwise, it does not generalize well. Also, trackers, in perception trackers, they can estimate things like rate of curvature and velocity and so on. They're continuous quantity that you don't want to really quantize because you lose accuracy. Right, so there's a lot of these downsides. So a rethinking of the representation was needed. And so we switched to sparse real world state. First, this was presented in a paper called VectorNet. Ultimately, you consider the map elements and the past agent histories to all be polylines. But that requires rethinking the architecture. And so we rethought the architecture. We published a couple versions, VectorNet being the prime example. But now I'll present you the latest paper we're putting on Arxiv, I think, this week. This is work done a while back, but I think still it's very useful as a baseline for further advances in the field. So what did we do? We start with the road polylines in agent state history. So it's sparse continuous input. We have several factor decoders. So for the road geometry, right, and map, for your own trajectory history and for interactions with other agents. So we encode these using neural net modules. We fuse this and we apply the multipath predictor head, right? And now there's a question, well, for the design of these blue boxes, especially these four, what are the right choices? And in the literature, if you scour it, there's a whole bunch of approaches on behavior prediction, and everyone tries different things. And we created a large data set and ablated these, right? And I'll share with you the findings. So what works well in our experience is polylines for road encoding, recurrent neural nets or LSTMs for agent state history, and agent-centric pairwise LSTMs. Agent-centric means that for the agent you're predicting, you look relative to its position and orientation where all the agents are, right? And so you essentially embed their interactions using LSTMs and max pooling in that frame of reference, right? And for encoding, we found that several rounds of self-attention work really well. And we had introduced a version of low-rank cross-attention, which is in the paper. You can see details. This helps make it a little bit more efficient. And so, of course, a good behavior prediction model, just like a good detector, there's several other core things you can do. So we no longer rely on clustering to create anchors. Now the model can learn them directly. Training on TPUs in large batches improves results. Ensembling several heads, like bagging style, improves results. And over-predicting a set of trajectory and then performing clustering and non-max suppression, because a lot of behavior prediction metrics involve diversity as a component, also significantly improves results, right? And so this is a very simple performant baseline method that currently ranks actually first on the open data set and fourth on Argoverse, and is quite competitive with the top submissions there. And so, yeah, if you want to check out more, see a paper that will come out this week. Here's some examples of this model, which is extremely fast, applied to some agents on the Waymo open motion data set. There's some vehicles and pedestrians. You can see it predicts diverse set of futures up to 8 seconds. This video there's some pedestrians in the parking lot. There's some pedestrians on the sidewalks, and of course, vehicles, right? So that's what I'm going to say about this specific behavior prediction model. I mean, one question would be what's next here in this space in modeling, right? And I think in the last couple of years, there has been a dramatic improvement in the fields of NLP and computer vision, driven by models like GPT-3, right? And then EfficientNet and CodeNet and many others in computer vision. And there is a clear trend, right? And this trend is that very large neural net models trained on very large sources of available data can achieve very impressive results and generalize better, which is interesting. And so, of course, I believe that a lot of these learnings transfer to our domain, right? And so we have several different platforms for data collection. We collect data from different environments and conditions. And traditionally in the classical stack, this would be a challenge to the human expert, because they need to design rules for all these different environments and logic. And here, if you want to use a large capacity model, all this diverse data actually helps the larger model be better at generalization, right? So it's actually beneficial, and it's really interesting transformation. And I think that really also makes machine learning more appealing, right? And we're seeing already and benefiting from some of these synergies of scale now. So compared to surface streets, say truck driving is a lot less eventful, right? You can drive mostly on highways and things rarely happen. And so we find that the models improve for trucks, say behavior prediction, like they can improve 85% of the data that we use for trucks for behavior prediction is collected from cars, and that actually is beneficial, right? And so this is an example of cross-platform generalization, and the same is true for the different environments, right? And relying more on large capacity models is fruitful in this way, right? And then the other part of this is that different models scale differently as the data increases, and generally models that have more transformer or self-attention layers fare better. And so there is a push to add more of this type of layers to our models. I showed that we have some, but you can go further, right? So there is a paper we put on Arxiv. This is a collaboration with Google Brain and Waymo called Scene Transformer that takes the transformer. That's an all transformer model for behavior prediction and conditional behavior prediction, and even suggesting trajectories for the autonomous vehicle, right? There is a elegant way to pose all these problems and define a transformer model. Of course, there can be many variants of transformer models, but that's one strong initial baseline. So the second thing I want to talk about is, so we have architectures, right? And they're scaling. Now, how do we scale our data demands for these models, right? And here's the law of scaling, right? I mean, better model architectures help to generalize better, right? And transformer layers help and all of this. Now, within a given architecture class, as you scale up the model parameters and layers themselves, you need to also scale the data you're training. All right, so we have this large fleet, and it collects a lot of unlabeled data, right? There's thousands of years, if not more, of driving. And this unlabeled sensor data swarm dwarfs the one that is human labeled, right? And you have all these intermediate outputs in your stack. People can label them, but it's expensive, right? And so the trend is, well, let's try to use more data and more unlabeled data and continue improving your models, right? So this is data research. It's actually extremely important in industry. If anything, it's more impactful than model architecture research, right? And I will show you just a few highlights of work we've done recently, just to give an intuition for the kind of things one needs to do to get the models to work really well, right? And so one of them is auto-labeling. So this is a version of the teacher-student training paradigm. So you want to, that's a successful paradigm in the last couple of years. So you have some powerful teacher model that distills a student model, and the student model would, I mean, a teacher can be much larger or be an ensemble and so on. The student ends up being a lot stronger than training it directly on the same data, right? And so this work of ours tries to adapt this teacher to our domain, which is rich and temporal. And so the question is, okay, what is the most powerful teacher we can think of? And to do this, when you're labeling, you can take advantage of two things. One of them is models can, when labeling, models can also look in the future, not just in the past. That's okay. Second, when labeling, the models can be a lot slower. They're not constrained by real time, right? So you can do better than your online stack. And so we have a paper in CVPR this year that proposes a specific instantiation of such an offline teacher. And it essentially is consists of two parts. One of them is we detect the objects using a detector that also peaks in the future. And then we track and collect evidence for each object over tens to hundreds of frames. And we estimate the final trajectory in light of all this tracked data. And what that allows us to do is to do really accurate shape estimation after you've seen say, a vehicle or pedestrian from all sides, right? Which is guaranteed over a long period of time. And so the resulting system can do really well on complex scenes, such as this one on the Waymo open motion dataset. I'll play it one more time. A lot of the data for the motion dataset, which is 100,000 sequences of tracks over a long time, is generated by this method. So now getting back to the case of, well, getting the models better in this teacher-student setting, one thing we show in the paper is that in the Waymo open dataset, if you train with 10% human labels and an auto-labeling model, use it to label 90% of the rest of the data, and then train on that, we almost recover the full performance, right? Not quite, but close. And similarly, we find this type of off-board teacher very promising for unsupervised domain adaptation. So if you train, say, on sunny San Francisco and Phoenix, mostly sunny, and then try to do well on rainy Kirkland, this type of off-board teacher helps a lot, right? Compared to the naive solution of just training or fine-tuning directly a model. So auto-labeling is great, but ultimately, it's not a panacea for the super rare examples. Like if an example is really rare, you may not even see it in your 10%. Ultimately, the rare examples you want to wring the most out of. And one way to do this is data augmentation. So you can apply all kinds of perturbations to rare examples, right? And that improves model performance on those. Now, we have some work exploring how to best do this. One challenge of doing this in the LiDAR domain, of course, in cameras, it's similar, is that there's a large set of data augmentation transformation you could apply, and each of them has parameters. So you can end up with a dozen or a few dozen parameters that you need to tune. That's very effort intensive. And so we show how to leverage progressive population-based augmentation, which is an efficient AutoML method, to efficiently search the space of deformations which are most optimal to improve quality. And this pushes, say, some average precision curve for detection from the black lines here for vehicle and pedestrian to blue. And now this year, we have extended the work to also apply this data augmentation to unlabeled sequences, right? Not just the labeled ones where you understand where the boxes are, so you know how to crop objects. And the key to doing this, applying to unlabeled sequences, is you need to build a mechanism such that the model does not get hurt by a confirmation bias. And this is also uses a population-based augmentation, and ensembles helps a lot. We described this in a submission. Hopefully, we'll make it public soon, but you can see this pushes the curve even further from blue to orange. And so with a lot less data, you can do a lot better. I'll breeze through a couple more mechanisms that we have explored to make our models more scalable. One of them is self-supervision. I alluded to this before. This is the idea that if you have several intermediate outputs and you know a specific constraint that involves these outputs, you can push a loss through the models and improve them via this loss, right? And I'll give you a couple of examples of this. So in cameras, this is deep structure from motion type of constraint. If you have a frame and you know the depth of each pixel, you know the ego motion of the vehicle, and you know the 3D motion of all objects in the world, you can take all the pixels and transform them to the next frame. And then you can check if the next frame looks like what you thought. And if it doesn't, you can push a gradient through the model and improve it. And that's what we show. Also, you can do 3D detection and tracking as such a task. So if you have detections and you predict the motion of those detections to the next frame, well, you better detect those objects in the next frame where you predicted, right? Otherwise, you can push a loss. And we show that this method is effective, and this specific works allows you to potentially use several different models asynchronously and compute these constraints. I don't have more time to go into this, but if you're interested, you can check it out. And one last work I want to highlight shows a combination of a few of these ideas. So we can improve object detection by having an auxiliary input, which is this semantic points, which are points that are anywhere on the vehicle. and we try to predict them. So these are the red points, right? So you may see a subset of gray points, but you try to predict all the ones that should be there. And then you take the semantic points, and based on them, you train the detector box head, right? And so what that does is it homogenizes the appearance of the point cloud, even for occluded objects or for potentially, say, slightly different looking data like rain. And so it helps you do well on rare examples. And also this type of head allows you then to do interesting data augmentation by dropping different parts of these semantic points and still forcing the model to detect correctly the box. And so when you do this, we got top results on the Kitty benchmark, especially for medium and hard cases at the time when this work was done. It's at ICCV now. This was the best performing published work in 3D object detection on this small data set, right? Where a lot of this structure is beneficial. I mean, it's generally beneficial, but that was an illustration. So yeah, so now that we're getting to the third point I wanted to talk about, this one is a very exciting work on planning and simulation and applying machine learning to those tasks. So unlike the approaches to this point, which are mostly examples of supervised learning, the task of planning is to produce a sequence of actions that perform robustly in complex scenarios that can take tens of seconds or minutes, right? And that's a different setting, right? You're applying a policy for a few steps, and you want to make sure that throughout the whole scenario, you get some kind of robust behavior. And so first, before we get to learning such models, let's talk about the role of simulation in scalable testing, right? And so even though at Waymo we have a large fleet with human operators that can mitigate errors or issues in the driving system, we have Castle Air Force Base where you can enact rare scenarios of concern or interest and check that we're fine against them. Like that is still not as scalable to the rich set of things you may see in the real world, right? And so simulation is really key to evolving an autonomous driving stack. And we use it at scale at Waymo. Simulated scenarios don't really expire. You can apply different AV algorithm variants on them, right? And we can keep checking that, in a whole variety of rich cases, which we've seen a lot of, we can generate some in some cases, we do well. And so, simulation, of course, is super helpful in testing. Now the question I want to explore in this part of the talk is, okay, but it can also provide important supervision signal for machine learning algorithms, right? And so what that looks like is, or the way to formulate it is, as a learning from simulation task, right? So what is the goal? The goal is to combine the millions of miles of data we've collected in the real world with billions of miles of simulated data to create robust driving policies that we can ultimately deploy on real world AVs, right? And so on one hand, it's very promising and I think aligned with some of the advances of AI and ML in recent years, particularly those from DeepMind, because you can see in their work, one common theme is that simulation and synthetic data is a key component of building robust, strong policies. Now, applying similar ideas in autonomous driving is particularly challenging. Unlike the games of chess or Go, which have a simple and perfect simulator, right? In our case, the world dynamics are unknown. Evaluation metrics are tricky to define, especially in the long tail or rare cases. And the goal is to ultimately deploy on the physical system where there are lots of potential challenges to overcome, such as real-time constraints or domain mismatches. So one way I will talk about here to deal with these domain mismatches and challenges is to try to train the policy in the same manner in which it is deployed, right? And this requires something we call closed-loop simulation. Closed-loop simulation entails executing the agent policy in the simulated environment and adjusting it based on the generated outcomes. And there is at least 4 high-level criteria which are key to successfully learning from simulation. And I'll go over them in a little bit of detail. So there's world agent models, planning agent models, hardware acceleration, and agent environment realism. And so speaking of world agent models, I'll give you the motivator of why they're important. So here is my classic scenario. We collected some world, scene using the sensors on the green vehicle. That's why our vehicle, it drove, collected what happened around it. And now in simulator, we started doing something different, and we're now the cyan vehicle. And now as we're running the simulator, this oblivious pink car slammed straight into us because, well, at the time the log data was collected, there was nobody there, right? And so now we have a collision to deal with. This is, I mean, even though some human drivers are not that attentive, this is not really realistic. I mean, the gist is that through our actions, we affect the environment, which then reacts to us. So if you want to have an accurate simulator, now you need to also model the world transition and count the behavior of other agents, right? So this is a bit of a chicken and egg problem, right? So now you can say, okay, well, now to have good simulator for planning, we need to learn world agent models too, which also plan. And yes, that is true, right? Now, let's recap on a high level how a world agent model is different from planning models, right? And they're different primarily in what you want to optimize. So in the case of world agents, you look at overall distributional realism. So if you play out a scenario, right, and do a Turing test, whether it's with humans or computer algorithm, you should not be able to discriminate which are the real and which of the agents you replaced, right? So here is a short clip to give you some intuition. Yellow are the log agents as captured when we drove. Green is agents we replaced with the policy, right? Now, in the other case, the planning agent, here we only care about one single object, which is the autonomous vehicle. But we have a more complicated task in some sense of thinking of high-level mission goal and routing, right? Like you want to go from home to the store. So you want to push the vehicle to execute that route for you, right? And navigate it safely. And so here's an example of this. So blue dots specify a high-level route. And then the green vehicle here is our agent that tries to navigate around the stopped car and then also an oncoming car and so on, right? So that is a planning agent. Now back to world agents. Let me go to the right picture. Let me talk a bit about imitation learning approaches that we can use to build world agents, right? And I'll show you later how I apply similar techniques to planning agents. Most of the results I share today come from a paper that is currently in submission called Symphony: Learning Realistic and Diverse Agents for Autonomous Driving Simulation by Maximilian, Dewu, Alex, and Brandon White, and a few other folks. Right? And here we compare in this paper two baselines, which are behavior cloning and model-based adversarial imitation learning, and two modifications. I'll go in with details and I'll share our main findings. So now, most of you folks are probably familiar with behavior cloning, right? That's the simplest type of imitation learning where you start with a set of outline demonstrations and you train a model using purely supervised learning to learn to repeat the actions of the expert, right? Given the state. So unfortunately, behavior cloning models suffer from the well-known covariate shift, or what people at Waymo call it dagger problem. Errors in the policy can compound over time, and you end up in situations you have not really seen in training, and then your networks fail to generalize properly, and you can perform poorly. Last year at the NeurIPS workshop, Brandon White from Waymo introduced a clever mix of ideas that combine enhanced behavior cloning with adversarial imitation learning with tree search. So specifically, we can learn a model by mixing a discriminative loss, a search distillation loss, with the behavior cloning loss. And at inference time, we can further improve performance by running a beam search where we generate many different simulation rollouts And we use the learn discriminator to rank and select the most realistic looking ones, the ones that are closest to actually the actual data distribution. And you would throw away their likely runs, right? And that can significantly improve a method like behavior cloning on task like collision rate and overall time. So through this tree search and pruning with the discriminator, we can get significantly more robust policy. And just a couple words about the experimental setup. We have a data set of over 1 million training simulations, 10 seconds each, 10,000 test simulation that we give the initial pose, and then we roll out a simulation for 10 seconds, right? And we replace 2 logged objects here, and later I'll show results with 8 replaced objects. And so the main lesson here is tree search with discriminator helps. However, one challenge with applying such a method, which is also common to other adversarial techniques, is mode collapse. This can affect the diversity of behavior without simulations. So let me introduce another metric we defined called Curvature Jensen-Shannon Divergence, which we can use to measure distributional realism. So this Curvature JSD is a metric to compare 2 probability distributions of the average trajectory curvature between simulation and reference trajectories. So imagine you come to this 4-way intersection and you have 1/3 chance to go in 3 different directions, which you will see in the real world if you collect enough data, right? And so you can measure, you can collect the distribution of curvature of trajectories as agents pass through many such points, right? And it may look something like this. And we can compare what happened in logs to the distribution that our policy with the method I described executes, right? And what you can see in this case, when you compute the Jensen-Shannon divergence, that it's worse. And specifically, our policy doesn't like making right turns nearly as much, right? And so that's the kind of mode collapse. And so the question is, how do we mitigate this mode collapse now, right? And one thing we can do to mitigate it is use a hierarchical goal policy. So the way this works is we learn a 2-stage model, right? So given the initial route, given the initial state, right, like we predict a goal, which here is a route, effectively a set of lane segments in the map. And those lane segments become waypoint features, which we condition both our policy and discriminator. Right. So first we select out of a possible route, and then conditioned from the route, we produce the policy. We run our policy and discriminator. And so the net result is that this hierarchical policy helps restore diversity, and we can see this experimentally. Now, when we've added both research and hierarchical goal policy, we're doing really well in collision rate and overall time, but we also fixed that, actually improved our diversity compared to even the baseline behavior. And while have been getting strong results with that approach, we also wanted to explore if there's ways to simplify the policy by training closed loop, but more end-to-end, and avoiding the computation of the tree search at inference time. And so we can do that with model-based generative adversarial imitation learning, or MGAIL. So the goal of MGAIL is to use a differentiable forward model to allow end-to-end optimization from discriminator to policy, right? And this avoids some of the high variance policy gradient updates of the original GAIL work. And so one of the learnings we have is that even without tree search, MGAIL has actually significantly better performance in robustness. And even though we expected a degradation in mode collapse of diversity, it actually performs surprisingly good there for 2 agents, but we see still a bit the effect for a larger number of agents, right? But still, even out of the box, MGAIL is pretty good. And now when we add all the bells and whistles, which are tree search and hierarchical goals, their effect on MGAIL policies is very similar to that of behavior cloning, and the two end up being pretty close, even though what we see empirically is behavior cloning augmented with research and hierarchical goals in our case is still quite powerful, right? And so let me see, and this is now armed with such agent models, we can take the same situation and potentially play it into different ways. There's exactly the same starting condition to very different rollouts, and we can generate potentially hundreds to thousands of different rollouts of a scene and learn from them, right? So it's a very interesting way to scale the type of data you have using simulation for learning, right? So that's what I can say about it. I think we're starting to run out of time soon a little bit. So I'll just talk about the other pillars here quickly. So planning agent is, of course, a core part of the task. Here, one of the key properties is we need to be able to define a route and condition on it. I'll show you one approach we experimented with, which is MGAL plus route conditioning. When you do this, very similar. So you can get a route by, well, you can plan a trajectory in the map using A-star search or pre-compute it offboard. You can represent the route as a set of, as a polyline really, across the lane segment. And we can apply an encoder on that, compute route features, and fuse this with agent and road graph features similar to other models I showed earlier in the talk. And that can generate a purely imitative planning policy. And it already does quite powerfully. So the example I showed you, this is MGAL, right, route conditioned, does quite well in complex situations like this. And if you compare to pure behavior cloning, that gets stuck in the very same situation and does not make progress. So, this is an example next of how we can change the goals of a vehicle and control it to do very different things. So in the real world, the dark green was what happened, and we gave the blue route, and our vehicle just, of course, executes that instead, right? So we have a lot of control of these agents, learned agents. Last two things. So I hope I convinced you a bit in the promise of closed loop simulation and learning. Now, to make it practical, we need to think carefully about compute. And just like, you know, most deep learning models benefit from hardware acceleration like TPU and GPU, we believe that hardware acceleration is necessary not just for the model learning and inference for the planner, but we want to run the whole stack in simulation using hardware acceleration and skip the slow CPU to TPU or GPU bottlenecks that are typical in some of the current reinforcement learning setups, right? And this may seem like extreme requirements at first, but I think you've seen over the years, and that's what I certainly have seen over my like 6 years in autonomous driving, is a lot of parts of the stack move to machine learning based models implemented in common graph language frameworks like TensorFlow. And I think that doesn't mean that the whole stack is a big ML model, but we could implement it all to run efficiently on accelerators. And once that is the case, then accelerator-based simulator is also very, very appealing. Okay? So something to think about. And last but not least, you know, if we want to minimize the domain gap between the learn policies and in the simulator and the real vehicle, of course, we want the inputs to the agent in the simulator to be as similar or as indistinguishable as possible to those that it puts in the real world, right? And so there is same sensor data, or if you have a modular output, maybe at least same perception outputs need to be given to the model in the simulator or as similar as possible as in the real world, right? And at Waymo, we of course have powerful sensors that allow us to reconstruct the environment in very high fidelity, as this circle map here shows, and can be centimeter accurate over hundreds of meters. Of course, out of this, we can build simulated environments. I'll just show you a short video here. On the left is the real data. The right screen split is the same version of the same environment with vehicles and assets replaced, right? And we'll leverage here Google mapping models. And of course, we can render this environment in many different conditions like fog and rains and so on. And last but not least, I want to show you a different way of building a simulator. So this is some early results from a collaboration we have with Google Research, which is a simulation environment generated by a machine learned NERF model. This is based on novel work of ours, which allows us to build 3D models of environments of arbitrary size, for example, entire cities. And I'll show you an example of what's a NERF model simulation looks like. You can tell it's a simulation because in the real world, no one will drive through cars in the parking lot. So we deliberately jiggled around the viewpoint to show you what is possible, right? This is entirely machine learned and then generated by queries to the model. And you can do the same thing for assets in the environment. So here are some objects with some of them are more interesting geometry that we learn the construction from with a similar type of approach, right? And so to summarize, I showed you 4 pillars of making learning from simulation possible, which I think can significantly scale the robustness of learned agents. And also I want to show you, I mean, ultimately in this case, there's a promising vision of how you can use ML to pull ourselves by the bootstraps. So we would spin the virtual cycle of collecting data, building a simulator to train agents, right, with imitation learning. Then we train an EV model in that simulator with some combination of imitation learning and RL techniques. And then we close the loop. We put this model in the real world, we collect more data, and we repeat, right? And so we are actively setting and exploring this virtuous cycle, and I look forward to sharing more progress with you in future venues. This is the recap of the talk. And I wanted to give you a plug about the Waymo open dataset. We shared a lot of the data that can make research in tasks like the one I described easier. And so if you're interested, go check it out at waymo.com open. And thank you. Thanks for your attention.
Thank you so much, Drago. I know we're a little over, but do you have a few minutes for a few questions?
Yeah, definitely. I apologize, maybe a bit long, but hopefully it was interesting.
No, it's okay. This was super informative, interesting talk. So we just have a few, and then we
so Matt, I just also want to say thank you, Drago, for being here and sharing all these very interesting insights and behind the scenes ideas. We greatly appreciate it. Matt, over to you to manage the questions.
Awesome. Thank you so much, Daniela. One of the questions we received for you, if you could elaborate on the technical stack used to perform ML at scale, how would you use the stack to perform camera and radar sensor fusion?
So ultimately, right, there's different ways to do sensor fusion. There's several, desiderata when designing the optimal way to do this. I think if you take any reasonably small data set, right, and you try to do sensor fusion, you can do better by doing early fusion. However, if you want robust performance on rare examples and robustness to sensor failures and so on, it's beneficial to do late fusion. And so there's some very interesting questions of potentially want to do both. Camera and radar are very complementary sensors, and maybe you want to do early fusion with those. Maybe lighter camera is also a great way to do it. You need to pick, ultimately, I think you need to have at least a couple of orthogonal channels that you late fuse, but in those you can still use early fusion. And I think we have some work currently on novel methods of fusion. As methods such as pseudo-lidar and lift splat shoot and others have become popular in the last 6 to 12 months, computer vision is becoming a lot more natively 3D in the way you would approach it. I think the traditional ways is you track 2D boxes and then eventually you ground them in 3D. Now you can look at it more holistically and densely. And so there's a lot more parallel between the different modalities. There's honestly a lot of different options. And I think there's a few desiderata though of you probably want some early fusion, you probably want some late fusion. You need to think which modalities to do this with. and then apply cutting edge models. There's a lot of good work how to say fuse camera radar. You can do a camera lidar too. Yeah, and we have some. Does that answer enough, or anything specific more that I should chime in?
No, I think that was really a great answer. Thank you. And another question we received, what is your approach to updating maps, and how persistent are these changes over time, such as a disabled vehicle or roadwork or rerouting?
So we don't have to update the maps all the time. I mean, ultimately, I would say that my attention is more on making sure that our methods are robust to errors in the map, because you're always going to run into them at some first time, right? That said, we do send routing information and updates to other vehicles the moment we've identified potential issues, right? Like if there is bottlenecks, if there is stop traffic, right? These are things that other vehicles can benefit knowing.
Oh, great. Thank you. And then a final question. Someone posted, autonomous driving involves sequential decision-making at its best. Would Waymo ever use deep reinforcement learning in its tech stack?
I mean, I think some of this work I presented is related to deep reinforcement learning, right? I think one of the challenges of using reinforcement learning directly is that you first need to have a simulator you trust, right? And so you need to bootstrap things quite significantly with imitation learning first, because pure reinforcement learning methods, otherwise it's not clear what you're optimizing, right? So you're optimizing and iterating both on your simulator and agent in simulator, which is a very interesting setup.
Thank you. And then this will be the last question. Are you able to comment on the overall progress towards the ability to match human performance, for example, in more challenging weather or construction?
I mean, I think we're making very reasonable improvements. I think the state of the art and our capabilities is increasing, as we keep iterating on the stack. And so I don't see anything particularly different or challenging in construction or weather compared to the problems we're already solving. It's a matter of more time and iteration, I believe.
Awesome. Well, thank you so much, Drago, for your presentation today.
Thank you guys for having me.